All right, hi everyone. It's my pleasure to introduce Sergey Samsonov today. Sergey is a PhD student at the HSE University. He's very close to graduating, he told me, and he's interested in sampling methods, reinforcement learning in general, stochastic approximation, also MCMC methods in general, but in the context of reinforcement learning. And today he's talking about a very hard problem, a finite time analysis of TD learning. So I'm very much looking forward to this talk, and please, Sergey, go ahead.
Okay, so thank you very much, Johannes. It was my great pleasure to accept your invitation to give a talk at the seminar. So yeah, please, during my talk, feel free to interrupt me to ask questions if you wish. So I think it's better to interrupt than to write in the chat because I'm not sure that I will be very careful monitoring the chat. So. Okay, my talk today will be on the finite sample analysis of the temporal difference learning. I will give the reference to the paper at the end of my talk. It is submitted to COLD this year. So it is a joint work with Daniel Tepkin, Eric Moulinet, and Alexei Naumov. Daniel is a former student of our lab at High School of Economics, and we worked a lot together with Alexei and with Eric on different problems related to stochastic approximation, so I should give them a lot of credit for this work. Okay, so I will begin with the general setting, introducing the problem of linear stochastic approximation, and I will provide some refined bounds for the error of the tail averaged iterates of the linear stochastic approximation. And then I will switch to TD learning and to how these bounds apply in this particular setting. So like first maybe 20 minutes of the talk, they will be related rather to the general LSA. And okay, if we start the general setting of stochastic approximation, of course it is familiar to you. We want to find such theta star that function f of theta star equals 0. So it is root of some nonlinear equation. We don't observe the function f itself, but we have some oracle which produces us unbiased or at least asymptotically unbiased observations in a sense that we have something which allows us to approximate the value of the function at a fixed point theta. And here we have a famous Robbins-Monroe procedure in order to solve this type of equations. So it goes back to the seminal paper of 1951. And most of the, okay, not most, all the subsequent talk will be concerned with a more particular problem when, in fact, our function f is linear. So in this case, we aim to find the solution theta star of a system of equation, a bar theta star equal b bar. We don't have access neither to bar b nor to bar a, but we have some sequence of matrix valued observations that allows to estimate a bar or b bar. Of course, this is exactly the setting, for example, of temporal difference learning with linear function approximation, but I will discuss particular examples later. And the LSA algorithm writes as follows. So you iteratively update your current estimate of the parameter theta k according to the recurrence 1 given on the slide. And it is also a commonly known thing that you can stabilize your training if you use the so-called Pollack-Rupert or Pollack-Yuditsky-Rupert averaging. That is, you simply average iterations theta k that come from a single trajectory. In such a case, so basically this technique goes back to the work of Rupert of 1988 and Boris Theodorovich Polyak with Anatoly Yuditsky in 1992. Unfortunately, Boris Theodorovich passed away the previous year, but I had some opportunity to know him personally. So if we go to the analysis of the linear stochastic approximation, basically we need to cover the two most maybe common situations on the regarding our assumptions on the sequence of noise variables at k. So they are assumed either to be IID observations or to form a Markov chain, and with unique invariant distribution, such that asymptotically the expectation of this matrix or vector valued functions a and b is correct. So it gives you exactly the left-hand side and right-hand side of your system. Okay, so I will proceed with LSA error bounds. And here we will introduce our first key quantity, the noise variable epsilon z, which is defined on the slide. So it naturally appears when we start to run the recurrence 2 for the iterates of the linear stochastic approximation. In such a case, you can think about the variable epsilon as something which measures the effective noise level at the optimal point, theta star. So you should remember that in principle, these random variables epsilon are non-observable in practice because you don't have access to the parameter theta star. But the quantity which matters is its covariance matrix sigma epsilon, because it is related to the CLT associated to our Polyak-Rupert average theta rates, and the quantity epsilon of z itself. So from now on, we will assume that both the random matrix A and its centered counterpart, A tilde, which is just the same guy centered by its expectation, are bounded, almost surely. And moreover, we will assume that the matrix minus bar A is Hurwitz. This means that all the eigenvalues of the matrix A bar have a positive real part of the spectrum. So as a second assumption, we will assume that our observations A for the system matrix A and for the right-hand side B are unbiased. So recall that for now we consider only an IID setting for the noise. We will also assume that the noise variables epsilon are almost sure bounded. But at the same time, this assumption can be relaxed to a moment type bound. But for simplicity, we keep everything bounded. So this is the running assumption A1 that will be translated later. And in this case, what we can do, if we run simply the recurrence for the sequence theta n minus theta star till the starting point theta 0, then we can have the following useful decomposition for the error of the LSA. It's not original, this decomposition has been known before, but basically it allows us to decompose the error of our algorithm into two parts. The first one is the transient component related to the rate at which we forget the initial error related with theta 0 minus theta star. And the second part here is the theta n fluctuation, which basically is responsible for the fluctuations of our solution in the vicinity of the optimal point theta star. So these two terms, it is somehow convenient to analyze them separately. Note that starting from this particular slide, I have put constant step size in our procedure. which will somehow change the behavior of our iterates. Of course, most of the results that I will present today can be translated also to the algorithms with decreasing step size. However, constant step size allows you, of course, first of all, you can always mimic the behavior of decreasing step size if you simply know, for example, the total computational budgets, that is the number of iterations that you are willing to write your algorithm, and then you simply adjust your step size alpha to this number of observations n. That's, of course, that you always can do. But trying to do this or trying to do decreasing step size will be somehow suboptimal in a sense how the initial error, that is how the term theta tilde transient, decreases with the growth of n. So in fact, decreasing step size, which of course is often used, will unavoidably yield suboptimal decay for this transient term. So instead of this, we put the constant step size, and then we will discuss some phenomena that arise from this.
Sergey, just quickly, I'm not seeing your screen anymore. Is anyone else having the same problem?
Oops. Really?
It works well for me.
It works for you?
I can see the screen as well, yeah.
Okay, it's just on my end then. Okay.
I can see it.
Okay, so
okay, cool. Sorry about that then.
Okay. Yeah. So from this decomposition of the error, it is clear that the essence, or maybe not the essence, but one of really the key points of the analysis of such a procedure is somehow to obtain the bound on the product of random matrices, which is defined by gamma mn alpha here on the slide. If we can have a high probability bound for this quantity, then basically our analysis looks like to be almost done, because then we can use a special structure of theta and tilde fluctuation. In fact, it is a martingale difference in case of independent observations, and then everything goes smoothly. But the main problem is how to control, for example, the p moment or p norm of the operator norm of this product of random matrices. And here is, very bad, sorry. Yes, I will not use touch bar for screening. So for now, for the general analysis of LSA, we will just put the following assumption, A2, which depends upon the parameter P, which exactly guarantees us the stability of the moments of the norm of this product of random matrices up to order P, basically. So this assumption states that, okay, for some parameter A, that is crucial because then it will translate in all our bounds. For some constant kappa P, it can depend upon P, and some quantity alpha P infinity, which depends upon the maximal controlled moment P, and alpha P infinity plays a role of the stability threshold, if you wish, such that the product of alpha P infinity times P is less than 1/2. In fact, this bound is more or less arbitrary, so it's for computational, more or less it's for theoretical simplicity. So you can somehow get rid of it, but you know that in general alpha P infinity should be related with P, because with constant step size you cannot have stability for all moment iterator norm of this product of random matrices. So in this case, we have exponential contraction with the rate which is controlled by this parameter A. And here, to avoid switching to the operator norm directly, I put the condition in maybe a bit strange way, because, okay, instead of controlling the operator norm, I prefer to control just a Euclidean norm of products of these random matrices times any vector u from Rd, or it is essentially the same as to have the control for the same product times the random vector, which is independent of the randomness, which is inside gamma 1 and alpha. Of course, this assumption is, okay, maybe it looks a bit unfair to assume it directly. And of course, there is a, okay, I again forgot that I should not do it. There is a well-established tool for checking assumption A2, which is applicable in the problems of general stochastic approximation, which is based on the so-called Lyapunov equation. So basically, yeah, if you want to have exponential stability, for example, in the form which is provided on the slide, it is almost the same as we had in our assumption A2. One of the ways to proceed is, in fact, to show somehow that this product of random matrices gamma m and alpha behaves similarly to the product of deterministic matrices, identity minus alpha a bar to the power n minus m, for example. You have n minus m terms to the left and n minus m terms to the right. If you somehow manage to do it, then it's okay. This approach can be leveraged both to independent and Markov dependency in your data. And it requires to switch from the operator norm to the so-called Q norm, which is associated with the solution to the Lyapunov equation with matrix A bar. So it is provided on the slide. We know that for Hurwitz matrices A bar, this equation has a unique symmetric positive definite solution. And then we can define these parameters small a and also the stability threshold alpha infinity such that our product of deterministic matrices is a strict contraction, but not in the operator norm, but only in the matrix Q norm. But okay, at the end of the day, it's not a big deal. You can always once pay the condition number of the matrix Q when you switch between different matrix norms. This is some general recipe. So in general, if you go to, if you want to go this way and to check the assumption A2 based on general properties of LSA problem, like Hurwitzness of the matrix, you will have some problems. So I provide this result for the sake of completeness. We will not use it for TD learning. Its main problem is the following. So this result, it is based on the wonderful paper on the matrix stability by Huang, Rachel Ward, and Trop, if I'm not mistaken. First of all, it seems that the dependence on dimension is unavoidable in such type of if such type of technique is used. And second, when you proceed to operator norm instead of controlling the norm of matrix vector product, you unavoidably have to rescale your step size together with instance-dependent quantities. For example, here from the result which is presented on the slide, you have to adjust your step size together with not only the maximal controlled moment Q, which you cannot escape, but also with BQ, which is related to the condition number of the solution to Lyapunov equation, and also with the threshold parameter small a, which is exactly the parameter coming in the contraction rate for the product of deterministic matrices. And of course, all of these parameters are known in practice. So you cannot normally you cannot adjust the step size in such a way. So this approach, okay, in principle, it gives you opportunity to check the assumption A2, but you will do it in some way that will not allow you to have really instance-independent bounds. So we will proceed, instead for TD learning, we will proceed with another type of technique, which allows us to avoid Hurwitzness completely and just to check the exponential stability directly. Okay, so are there any questions for now? Okay, so if not,
sorry, just maybe one. So the main question is how to choose the step size, or
yes, that's really the main question, because all our previous stability arguments will not allow us, for instance, independent choice of the step size. So okay, you can check stability, but you will check it with the bound on the step size that depends on this unknown matrix Q. That's typically, of course, in practice, you never compute Q in such type of problem.
So what is Q exactly? Is that something that I can choose?
Sorry?
Is Q defined somehow, or is it something I can choose?
Q is the solution of Lyapunov equation. So it is the Lyapunov equation, which I'm showing now on the slide. Lyapunov equation associated to A bar. So in principle, there is some degree of freedom that to the right-hand side, you can put not identity, but you can put any symmetric positive definite matrix. So and then the rate of contraction will also depend on which matrix you put here. But typically, it does not make life much easier.
And the linear TD setting really just maps 1-to-1 to this.
And you can check all this to the linear TD, but the results that you obtain within this approach will be more rough than the main results that I will present later. So you will not have instance-independent choice of step size if you do this.
Also, I'd like to ask, in the last result, the last theorem.
Which one?
Yeah, this one. You are showing a condition that is actually a bit stronger than your assumption, because here you're bounding the full norm of the matrix instead of the norm times U, right?
That's true. Yes.
Okay.
Yes, that's true. But unfortunately, or maybe not unfortunately, but typically when you proceed with this with the technique based on Hurwitzness, that's what you do. So you have something stronger. So instead of controlling the images of the product of random matrices times some vector, you control the operator norm. And this is probably, I'm not 100% sure, but probably this explains why, for example, here you have explicit dependence on dimension. At least the techniques that I know to obtain this type of result yield the explicit dependence on dimension. While in our setting for TD, we will be able to have the result which does not depend explicitly on D. So maybe this is related directly to the fact that, in fact, we don't need to control operator norm to prove, for example, bounds for the transient term of the error. Okay, so now the refined LSA error bounds. So if you consider the second moment of your error under assumptions A1 and A2 with parameter 2, so you can control only up to the second moment of your error. You can have the following result. The second norm, okay, it is for when you consider Pollock-Rupert averaging, it is very classical to have a bar to the left. So to consider the norm of theta n bar minus theta star, which is rescaled by the system matrix A bar. Of course, in practice, it is unknown. But if you wish, it is not a problem to rescale everything by A bar minus 1, and then it will change, of course, the leading term in our bound. It will be not trace of sigma epsilon, but it will be trace of A bar minus 1, sigma epsilon, A bar minus 1 transpose. So it is just like the multiplication of Gaussian by some fixed matrix. So note here that the leading term of the bound, the square root of trace sigma epsilon divided by n1/2, it basically aligns with the central limit theorem for LSA with Pollock-Rupert averaging, up to this additional term that I have in the bracket. So you have optimal term from CLT times 1 plus something which can be small. If, for example, I put alpha, which is instant dependent, for example, alpha scales with small a, Or if I, for example, if I try to adjust alpha together with the total number of iterations n. For example, I put like alpha, something like 1 divided by square root n or something like this. Otherwise, note that my technique with constant step size potentially can spoil the leading term in the CLT. Because it's possible, okay, if I don't adjust alpha with A, and if A is really small, for example, some minimum eigenvalue of some matrix that you never observe, then you really might have problems with this term. Everything else are fine. So, for example, the second term is of order 1 over n, and then you have something which decays exponentially fast. And for the p moment, you can have exactly the same. Basically, you translate the same type of the bound for the p moment. Here you have Gaussian moment behavior. So your leading term scales as p1/2 times square root of trace sigma epsilon divided by n1/2. Again, times 1 plus some correction, which depends upon the ratio between alpha and A, and which again can be not small, provided that alpha is instance independent. Otherwise, this large O of p divided by n you can make explicit, but its behavior is okay from the non-asymptotic point of view. And here you have again exponential decaying transition term. So again, the main thing that I want to emphasize is that really with the constant step size, you might have some potential problems with the leading term. And in TD, we will see that it's exactly the case. So here, to have this bound, basically we need that alpha scales as, since it is p plus log n infinity, you can think that the step size that you have here should scale inversely with p plus log n, basically. And note also that this result is completely dimension-free. So there is no explicit dependence on dimension, for example, here in large O of p divided by n. So the only place where dimension can appear is this constant kappa from the matrix stability. So if you were not lucky enough to check assumption A2 with dimension-free constant kappa, then you may have a problem from this term. Otherwise, our result will be dimension-free. Yeah, so that's what I just told. So in general, it can scale with D. And in case of TD, we will not have this problem. And yeah, one way to mitigate the problem with this additional term is really to set alpha, which scales with our available computation. But then our rate of forgetting the initial error, theta 0 minus theta star, will be suboptimal. Okay. So the rest part of my talk will be devoted to the application of these bounds to the setting of TD with linear function approximation. So yeah, if you have any questions regarding the previous part, probably it's time to have them now. I will show them in result.
So you mentioned that with a constant step size, you might have this problem of the this inverse of the instance dependent quantity. Like,
yes,
was it A?
You can spoil the you can spoil the leading term from CLT. Exactly.
So why are you aiming for a constant step size? Why not a decaying one?
With the decaying step size is also interesting, of course. But if you do decaying step size, then you will not have optimal rate of forgetting theta 0 minus theta star.
Okay, yes.
Okay, that's
here it's clear. But you do have some buffer, right?
Sorry?
Can you go back to this formula? I'm still parsing this. Because those terms are 1 over n.
The second term, the last term is exponential. It should be exponential because yeah, we want to forget initial error at the exponential rate.
So why do you want to forget the initial error at exponential rate? Why not at 1 over square root n?
Yeah, of course, it's possible to have. If we are ready to sacrifice the exponential speed of forgetting, for example, of this guy to the polynomial 1, yeah, then okay, then we can proceed with, for example, with decreasing step size, and then then it will be less painful to deal with, for example, R1. Yeah, that's true.
Okay.
Because it will be at lower scale. Okay, so now we switch to TD. So we have the Markov decision process with a tuple, state space, action space, P, which is a transition kernel, reward function, discount factor gamma. We will not assume that S or A are finite, so it will be okay if they are all complete metric spaces with some Borel sigma algebras. We will assume that the reward function is deterministic, and we will assume that we want to evaluate value function of some policy pi. So pi here is a pi of something given S is the distribution over the action space A. So in this case, we aim to estimate the value function, which is the expected discounted gain, provided that our agent follows the policy pi. Then in our condition, it will often appear the one-step transition kernel pi indexed by P. So this is the transition kernel over states. So basically, you just integrate out the policy pi in your kernel, which defines the environment. And we consider the setting of linear function approximation. So we will approximate Vp by V theta P, which is a scalar product of phi of S times theta, where phi is some feature mapping. We will assume that phi is fixed. So we will not learn the mapping phi itself. Once again, I'm doing it wrong. Sorry. Yes. In such a case, our problem of estimating value function reduces to estimating parameter theta. And this is exactly the LSA setting with the randomness given by pair sk and sk prime. And then we can write the corresponding LSA system. So this is exactly the setting of online TD. So we can exactly represent it as an instance of LSA. And then we can have some respective deterministic system, which is A bar theta star equal B bar, with explicit expressions for A bar and B bar. But okay, so we will not use them much. So it will be useful only to remember the updates 7 and 8.
Okay, so what is S prime K?
SK prime is the next state.
The next state.
Yeah, okay. You select some action AK and then you go to SK prime. Exactly.
And the tuples are like.
Yeah, for the tuples, I will say now.
Okay.
Yeah. So first we begin with independent setting, and then I will show how to generalize to the Markov case. So we begin with generative model assumption. So here our tuples of state, action, and next state are independent, with state S, which follows invariant distribution mu, and action, which follows our policy, and then S prime, which is generated by our environment. This is assumption TD1. We will then update it to have something more reasonable with truly Markovian dependence. We will assume that also that the design matrix sigma phi, it is defined on the screen. We will assume that it is non-degenerate and its minimum eigenvalue is positive. And moreover, we will assume that it is bounded by 1 in the operator norm. So we will assume that norm of our feature vectors phi is less than 1. This parameter is for simplicity. So if you just assume that it is bounded, you can trace exactly how it affects the bound. But And again, in principle, it should be possible to generalize this to moment type bounds, but it will make the subsequent generalization to the Markov chains more complicated. Okay, so in such case, theta star is also the solution of the following minimization problem. So in fact, it is arg minimum of the expectation of v theta pi minus v pi, where expectation is taken with respect to mu, which is a stationary distribution of our states, S. It is actually not hard to check this fact. And also it gives an idea that we are interested in the norm between, for example, two values, theta and theta star, which is driven by which is induced by the function sigma phi. So in fact, what we really want to measure is the expectation and the stationarity between our estimator v theta pi of s and the true best approximation in our linear collection of functions v pi theta star. And one can check that it is, if I write this expectation, it is simply norm of theta minus theta star generated by the matrix sigma phi. So it is simply matrix norm, which is defined by sigma phi. And then if we want to switch from the norm related with matrix A bar, we can use the lower bound, which is provided on the screen. So in fact, our bounds, which will be in terms of A bar times theta minus theta star, they can be translated to something which is in terms of the expected difference of value functions, with the payment that we have 1 minus gamma squared multiplied by lambda min. So this result, again, this particular bound existed before us, so we credit the paper of Li et al. From 2023. Okay, so now the previous results. So what is available for TD? There are some results in the framework of robust stochastic approximation. And this is a very famous paper of Bandari of 2018. So here, what they have in their paper is they have a result for constant step size, alpha, which is independent of problem conditioning. So it is completely realizable procedure. And the rate that they obtain is also completely independent of problem conditioning. It is 1 over square root n. But the problem is that if you look here, by the way, there is obviously a typo here. Okay, maybe not obviously, but the feature of robust stochastic approximation is that you have a mean squared error of order 1 divided by square root n. So it was my mistake to put the power 1/2 to the left-hand side of the equation. So in fact, you have really mean squared error, which you expect to be of order 1 over n. And within the framework of robust stochastic approximation, it is 1 over square root n. But you gain in terms of conditioning. So you should not think about this nasty lambda mean and so on. And then there are quite a lot of recent papers. So the paper by Patil and Doina Prekup, the last one, it is published on iStats 2023. They provided second moment bounds for TD0 and also high probability bounds, but with additional projection steps for TD. Basically, they have done it to avoid this arguing about matrix stability, to the best of my understanding. Then there are two papers, one published in Mathematics of Data Science, and the second is archive preprint, which basically provide high probability bounds and sample complexity for TD0. But so in one of the papers, the second one, the step size unavoidably scales with minimal eigenvalue of the feature matrix. And moreover, it covers only the IAD sampling. And in the second paper, there are only second moment bounds provided for, but there are also some matching lower bounds, and there are also nice results on the variance reduced version of TD, which allows to obtain the optimal variance term, but at a price that you do some additional learning of control variance. Okay, so now we will try to take best of all these worlds as far as we can. And yeah, here's the first, the first striking result, if you wish. Okay, I will probably better show it like this theorem. So we can check the matrix stability assumption A2 exactly for the choice of step size, which is problem independent. So it requires to know gamma, which is not a big deal, but it does not require any knowledge of lambda mean of design matrix. And it requires that the step size scales as 1 over p, where p is the maximal moment that we want to control. So this result is provided on the slide, and note that also this strange constant kappa that we were afraid to be dimension dependent. In fact, kappa equals 1 in this case. So you can have contraction in one step in this case. So if you take one random matrix, it already contracts you the norm of your initial error, which is very nice. And again, if we apply the general results based on Hurwitz's assumption, then we will have additional factor of lambda mean of sigma phi, which appears in 10, which will be then translated to our bounds on the transition term. Again, we will have suboptimal transition term if we do like this. Moreover, it is not nice in a sense that we don't know lambda mean in reality. Okay, but with this bound, you really have something reasonable. The constant 128, I'm not sure that it is optimal. Perhaps it can be improved. So I will skip the sketch of the proof for this idea, but if we have time at the end of my talk, I think I will go back here. And I will focus on the results for the second moment and for the p moment of the error. So first of all, if you want to consider the second moment of our TD error in the sigma phi norm, then we have the following result. Again, it is presented on the slide. The leading term here at a rate of 1 divided by square root n. Basically, this term is an upper bound for something which appears in the central limit theorem for our iterates. So I will be able to show you tighter version of theorem 2. But note that even here you have some clear problems. So roughly the first term of the bound corresponds to the first term of the bound corresponds to the variance of our iterates, and you see that it has scaling of square root alpha divided by square root of lambda mean. So again, okay, you fix some of the problems. You have the step size which is independent of conditioning, but you have this perturbation, which is maybe not small. But still, you have good rate of forgetting the initial error. So you can make everything explicit with respect to F1. So I will present now the same result as a sample complexity bound, and then we will discuss what's going on. So if I want to have the mean squared error less than epsilon squared, it requires to me to have the following number of iterates. It is provided on the slide. So basically, the first part of the variance, norm of theta star squared sigma phi plus 1 divided by 1 minus gamma squared lambda mean epsilon squared. This term is known to be optimal. And the main problem is that I rescale it by something which again contains the fraction of alpha divided by lambda mean. Then I have the term R1, which scales as 1 over epsilon, so it's for epsilon small enough, it's not important. And then I have the dependence on the initial error, which scales as 1 over alpha. And then here you have a nice trade-off. So if you take the step size alpha, which scales simply with 1 minus gamma, then you have a sample complexity bound, which agrees with the bound of Patil. And you have a variance term, which is suboptimal by a factor of lambda mean. At the same time, the rate of forgetting the deterministic error is believed to be optimal. So there is a lower bound for accelerated version of TD, which is 1 divided by 1 minus gamma times lambda mean times the same logarithmic factor. So it differs only by a factor of 1 minus gamma. But for sure, lambda mean should appear in this quantity. So I don't have really a lower bound, and I'm not aware of if it exists in the literature or not. But this setting, I more or less believe that the rate of forgetting deterministic error is optimal here. And then you have additional lambda mean invariance. And then if you set the step size, which is much smaller, so you rescale it with lambda mean, then you have suboptimal rate of forgetting the initial error, and then you have the variance term, which is perfect. And this is something which is reported also in the paper by Lee for the instance-dependent step size. And exactly the same translates to high probability error bounds. So we can have a p moment bound and then translate it to high probability bound using the Markov inequality. So here, perhaps the details here are less important. But if we try to optimize the sample complexity provided on the slide with respect to the step size alpha, we will have exactly the same type of dilemma. So either we take alpha very small, we scale it with lambda mean, and then we have suboptimal rate of forgetting the initial error. Or if we have maybe some proxy at least for lambda mean, then we can have optimal variance, but then we pay in the way how we estimate the attention term. So you cannot do best of both worlds, at least with vanilla TD. At least from our bounds, it doesn't fall. Okay, and now, so why these bounds are believed to be okay? You can have the optimal covariance matrix, sigma epsilon optimal, which is basically this is the covariance matrix of the TD procedure, rescaled by the system matrix A bar, and also the noise level sigma phi, not noise level, but design matrix sigma phi. This procedure is done to have to whiten basically the noise covariance inside the variable epsilon. If you do this, then you have exactly the matrix sigma epsilon optimal, which arrive for the CLT for the respective iterates of Pollock-Rupert for TD algorithm. And you can have the following result, which is refined theorem 2, where the leading term is exactly the variance of the respective Gaussian from CLT. And then you have the second order term, which again should be balanced for alpha with respect to lambda mean and perhaps with respect to sample size n. Again, if you don't adjust alpha with n, then you have problems, and through this term, apparently you might have suboptimal dependency in condition number when you proceed with bounding the variance of your iterates. But the leading term here is optimal. So it's optimal, it perfectly aligns the CLT. And now, so I suppose that I have 2 minutes. I will just briefly tell you how to proceed with the Markov setting. So recall that everything that we have discussed before, it was specific to our generative model assumption, where our tuples are sampled independently from the generative model, which is, of course, not very realistic. And instead, you can assume that you really have tuples which are generated sequentially. And in this case, the sequence SK from which you learn your TD agent is a Markov chain with a Markov kernel pi p. And then you can translate, you can have a counterparts of our bounds using the assumption that pi p is uniformly geometrically ergodic. Example. That means that it converges exponentially fast, its iterates converges exponentially fast to the invariant distribution mu in a total variation distance. And this convergence is uniform with respect to state S. So UG is rather strong. Again, one can imagine generalizations to other types of mixing, for example, to V-geometric ergodicity or to ergodicity constraints in Wasserstein metric or Wasserstein semi-metric. But such results become much more involved from the technical point of view. And in such a case, we will follow the idea of Nagaraj with co-authors from 2020. It is a new RIPS paper together with Patil and Prekup. So in this case, we can proceed in two different ways. The first and the simplest way is provided on the screen. Basically, we do TD learning with data drop. So we have some time window parameter Q, and we simply take every Q's observation from our generative model and simply get rid of all others. That's one option. For now, we will fix it, and then I will tell about the alternative. The main problem here is that if I want to apply it, then the optimal choice of the parameter Q is related with the mixing time of my chain of states. So the optimal choice is to set Q, which is exactly equal to Tmix. And in such case, I can have the result, which is an exact counterpart of what I have in the IAD setting. But both the variance term and the rate of forgetting the initial error are scaled by a factor of Tmix in this case. So roughly, this captures the idea of dependent observations. That okay, if you have mixing time Tmix, then roughly speaking, having n times Tmix dependent observations is something like just n independent observations. So that's exactly captured by the theorem 2. And the proof is very simple because basically it follows from Berby coupling lemma. And I can give you slightly more details if you wish, but after the end of the talk. And note that for this bound, the only thing that we pay is the extra factor of log 1 over delta in the leading term. So now this leading term becomes sub-exponential instead of sub-Gaussian. In the IAD setting, the same guy would be with square root of log 1 over delta, and it will not contain a factor of Tmix. If you don't want to do data drop, because it is maybe not the most intuitive thing, you can proceed with generalization of our stability argument from IAD setting. But in this case, you will have to adjust the step size of the procedure inversely with mixing time. So basically, appearance of the mixing time is unavoidable. Otherwise, if you don't adjust alpha inversely with Tmix, you will not have, unfortunately, you will not have exponential stability. And moreover, you know that the presence of mixing time in the bounds is not an artifact of the proof because there are respective lower bounds. And that's why the problem is that both the first generalization with data drop and the direct generalization would require to know mixing time. And of course, it is a limitation of our analysis for the Markov case. And that's why this is maybe one of the two open questions. Like, okay, is it possible to adapt somehow to mixing time here? So, okay, is it possible to proceed with some kind of adaptive version that will not require knowing Tmix? And then there is a question if our analysis for theorem 2 is really tight, for the case when the step size is independent of lambda mean. So is it possible, for example, to construct a lower bound that will show that this suboptimality for vanilla TD is not an artifact of the proof? And then it is really great because together with the control variates technique introduced by Lee, it shows that, okay, then vanilla TD without variance reduction is suboptimal. And then you do variance reduction, you have some implementable procedure, and then you have optimal variance term. So it will be like a complete story on TD. So that's all that I would like to say today. So there are two papers. Basically, the first one contains some discussion on the approach to the stability of product of random matrices based on the Lyapunov equation. And the second reference is the main one, which contains all the refined bounds for LSA and for TD learning, which is submitted to COIT, as I announced at the beginning. So thank you very much. If you have any questions, please let me know.
All right, thank you. Very interesting. Yeah, we certainly have time for questions. So maybe one thing I was wondering about. So there are also papers that, like in the setting of reinforcement learning with linear function approximation, there are papers that use more an experimental design type of approach where you try to construct like a spanning set of features and then you roll out episodes and you directly control the error of the least squares estimate. Are you familiar with these results and how they compare in terms of sample complexity and maybe how they compare in terms of, I don't know, advantages of one algorithm?
Good question, but I would say from the very beginning that I'm not familiar with this work. But so from what you say, it seems that okay. So basically, it is the question of the design fee, yeah. Because for example, I assume that the feature map is fixed, and of course, it is a large limitation because okay, it's not obvious that you can immediately come up from a good feature mapping from the very beginning. And of course, moreover, this sigma phi can be very bad conditioned and it directly affects the bound. So it's, but to the best of my understanding, what you are talking about is more related to the question of how well you can approximate the optimal value function by a given span. Yeah?
Okay, so then maybe I should just clarify. Are you assuming that the true value function is actually linear or you don't require this?
Yeah, here I don't require it. Because, okay, you know that your optimal parameter corresponds to the best approximation in the
I see. Okay.
Yeah, that's all.
And the approximation error?
Yeah, and the approximation error does not show up in my analysis. Yeah,
because you're just comparing to theta star, right? Yeah, okay.
All you do is comparing to theta star. Yeah.
Okay, so then this is definitely different in a way.
Exactly.
Because
of course, the approximation error is important because you can have sigma phi with which is very simple, with very simple feature mapping phi, such that it's easy to find the optimal solution theta star or to approximate it with reasonable quantity, but the approximation error is so large that it's completely useless to really run the algorithm, of course.
Great.